Okay, so today we're going to speak about Netlist. So Netlist is we use it to describe language, describe the language, the circuit. So here, for example, for an XOR, we try to describe it to the CMOS and PMOS level in order for the FPGA to understand what kind of what is the circuit. So in order to write this, we have to describe it as the descriptive language, and also write a Verilog code or a code that can describe this the language we have just written. And then so that's it. And for the normally for example for the big development tools like Quartz, VV, many most of the applications, this is built in. It's normally produced in this types of softwares. However, if you want to optimize the performance to the transistor level, in this case, you have to use other types of application like OpenFPGA or many other. In this example, explaining the FPGA spice, the spice regarding the netlists. So in this example, I'm doing the D-latch, which has additional set and reset. So uh, um, one is high and active high, and the other one will be low. So one will be inverted here, and the other one will not be will stay the same. The reset will be inverted, and then so this is our circuit that from a gate level. However, as I described before, we have to go to CMOS or PMOS. So for any circuit you have and you want to write down, normally you have to check how it's done. So the easiest way to just write it in form of gates, and then you have you have discovered the best architecture for each gate, the architecture that uses the least power or according to performance. So in this case, I have done the for the NAND gate as done before. So for the NAND gate, I created this. So for the NAND gate, for first of all, the inverted for the reset is here, and then since so this becomes the node 0, which is here. It goes to, for example, NAND gate, and then we have data that also goes to NAND gate, and then we have an input which comes from the other NAND. So we have data, and then there is the node coming out of here, for example. So this is not node 4 goes here as the input, and so on. So we have this as in my design. In our design, there is six NAND gates with an inverter with total of 19 PMOS and 19 NMOS. So this is for the second this NAND gate, and then the same thing. The most important to just write down also the nodes. You can even write them here so that you don't get confused, and then describe them here, the node, the inputs, reset, clock, and 10, so that you don't make any mistake. And then this is the final the last NAND gate, which is this one. And then we have two more gates over here. The final, this is um, so this gives the final output if we want Q, from which we can get a final Q. So let's start. So in order to write, I'll be starting just with the PMOS and then go to the MOS. Okay. In order to write a netlist, you have to go from drain, gate, source. So we have here for the PMOS, we have the drain, gate, and then source. So we have N0. Of course, you have to write it as the first line is disregarded normally in the netlist. So you can just write the name, write a star and just write a comment or the name of the function or anything, and then we use subcircuit in this, and then subcircuit and write everything in between, and then dot eom, and then we're going to name our the whole circuit as d latch, and then I have d, and I have set, I have reset, I have clock. Then I have VDD as ground and size equal 1. Then, as I said, for the first PMOS, which is this one. So for the first PMOS, we have N0, and then we have reset, which is the gate, then the source, which is VDD, then VDD, then the versatile place and routing for the PMOS, then the L equal PL. Afterwards, we have XP1, XP2, and XP3. So the XP1 and XP2 and XP3, as you see, first of all, we have the XP1. So XP1, we go from node 1 to D, VDD. And then we have XP2, which goes from node 1, node 0, VDD. Then we have XP3, we have N1, N4, VDD. Then take this and we go. So let's take a look at the next one. So we have here XP4, XP5, and XP6. As described before, so we have the node 4, then it goes to N1, so drain, source, gate, drain, gate, source, VDD. Then I have N4, clock, S, N4, N7, VDD. And then we have, because as PMOS, they are powered by VDD. So we write PMOS VDD, and then there is place and route for PMOS, and then the LPL. Afterwards, we're going to the next NAND gate. A second. Yes. Okay, for the next one, we have XP7, XP8, and XP9. So XP7 goes from N7 to N0, then goes to VDD. Then we have XP8, it goes from N7, clock, VDD. And then we have XP9. For XP9, we have N7, goes to N10, and then goes to VDD also. Then We have VP10. We have to move to VP10. So VP10, it goes from node 10, then goes to set, then goes to VDD. Then we have X for the XP11 goes from drain, so N10, N1 VDD. XP12 from N10, N7 goes to VDD. Then we have XP13, XP14, and XP15. So for XP13, it goes from N13 to N0 to VDD. X14, um, it goes from sorry, it goes from N13 to N4 to VDD. Then VDD, of course, VPR PMOS. We have for the last XP15, N13, N16 VDD. Then let's go to the last one, the last three PMOSs. We have XP16, XP17, XP18. XP17, XP6, let's start from XP16. So it goes from node 16, then goes to set, then goes to VDD. And XP17, it goes from N16, N7, VDD. XP18 goes from 16 to N13, then to VDD. So now we have done all the PMOS. Let's go and check the NMOS. So give you a minute to think about how to do the NMOS. The NMOS, drain, source, gate. Over the NMOS, it's opposite. So drain, source, drain, gate, source. Since we said before, here the source is what? Either the source normally was we charge it it's um, it needs ground in order for it to work. So in this example, in this we rather than VDD would be ground, and the VPR place and routing would be with NMOS, of course. Then the L equal N times L. I'll give you a minute to think about how to do for the first four here, and the other three. Okay, so for the XN0, XN0 is what? It's ground, reset, N0, no, it comes drain, source, gate. So N0, reset, ground. Then we have XN1. XN1 is what? N1, D, D, then N2. XN2 is N2, then goes to N0, N3. XN3 is N3, N4, then goes to ground. Okay, I'll leave you for example to do example 3. Okay, so here XN4. So what's XN4? XN4 is N4, N1, N5. XN5, N5, clock, N6. XN6, N6, N7, ground. And then as ground, of course, VPR, NMOS, L equal NL. Um, then I leave you to the to this example. Okay, so let's finish them quickly. So we have XN7, XN7, X07, reset, N8, XN8, N8, clock, N9. Then we have X9, N9, and then ground. Let's go for the next example. So in this example, we have SN10 is N10, set, N11 as ground, of course, VPR NMOS, NLL, XN11, N11, N1, N12, XN12, N12, N7, ground. Uh, Afterwards, we have XN13, which is N13, N0, N14, N14, N4, N15. X9 in XN15 and 15 and 16 ground. We have afterwards XN16, we have N17 set, N16, XN17, which is N18, N7, N8, N17. Then we have X19, which is N18, N13 ground. You can find here. And then we have to, since we finished the MMOS and PMOS, we have to write end of our circuit, so dot EOM.